Welcome to Complex Analysis, Lesson 21 on residue theory. Residue theory involves finding the integral of an analytic function over a contour where the function has singularities at a discrete number of points. I'm showing sort of a picture of that here. So we'll look at that. The evaluation of the integral depends on a number of items that we've studied leading up to this point. So this lesson has the secondary purpose of unifying a number of concepts that we've talked about before. The other thing I want to mention is this is probably the last lesson in the series, unless I get some request to add some additional items or I decide on my own to add some additional items. But for the time being, this is probably the last lesson in the series. So let's start this lesson by reviewing an example we did in lesson 17. What we're going to do here is generalize what we did in this example. So just to refresh your memory, let's go over what we did in the previous lesson. We had a contour gamma going about two singularities for a given function, which was otherwise analytic within the contour. And we broke the contour up into one part above the x-axis and one part below the x-axis. And then we found alternate contours that had the same initial and terminal point. And the reason for that was it was easier to evaluate the integral over these alternate contours. So for gamma sub 2, we defined this dotted line contour. And then for gamma sub 1, we also defined another dotted line contour. And by the deformation invariant theorem, the gamma sub 3 and gamma sub 2, when evaluated over f of z, our function in question, yields the same result. And the same thing here for gamma sub 1 and gamma sub 4. Now the advantage of doing this was that we noted that A cancels with the contour over x because they're going in opposite directions, and B cancels y, and C cancels z. So the integral over those three straight lines cancel each other, and we're left with this semicircle and then the rest of it here, and then this semicircle and the rest of it here. So the problem reduced to taking the contour integral over two circles, and we found that that was something we knew how to do based on yet another example further back. So we're going to do the same deal here in this lesson, except we're going to generalize this, and we're going to take a finite discrete number of points within a contour where the function in question is analytic other than at those points. At those points, the function has singularities. And we'll get to that in the next slide. As I said on the previous slide, we want to look at the general problem of a function f of z, which is analytic on and within a simple closed positively oriented contour, which I've drawn here on the right, except for a finite number of isolated singularities. So I've shown 3 here, and we'll work through the example with 3, but we'll give you a general formula for n singularities, and we'll see that in the next few slides. On this slide, I've taken over the contour gamma from the previous slide, and recall we had 3 singularities for our given function. And I know this looks kind of complicated, but it's the same thing we did in the example that I reviewed on the first slide. We first break the contour into gamma sub 1 and gamma sub 2. So gamma sub 1 goes between point w sub 2 and w sub 1, and gamma sub 2 goes between points w sub 1 and w sub 2. And then we want to replace gamma sub 1 and gamma sub 2 by these internal, I call them internal contours that are going just around the 3 singularities. So let's look at the gamma sub 1 first. we're going to replace that with a contour omega sub 1, then omega sub 2, which is a part of a circle, omega sub 3, then another part of a circle, omega sub 5, another part of a circle, omega sub 7. And by the deformation invariance theorem, the integral over gamma sub 1 and this omega contour, which I just went through here, basically going above the singularities. They have the function f of z has the same value over that contour. And then we do the same on the bottom. I won't read them all off, but I call them phi. And so collectively, phi sub 1, it's going this way. So phi sub 1, phi sub 2, so on. We'll call that phi. And that contour will replace gamma sub 2, and then omega is what I described initially. So a lot of words, but what we're doing is replacing gamma with these two contours, which are made up of yet simpler contours. Now the advantage is that you have a lot of cancellation here. So phi sub 1 and omega sub 7 cancel, or at least the integral over that cancel, because they're going in opposite directions. And then these two cancel, and these two cancel, and these two cancel, and you're just left with 3 circle contours, which we know how to evaluate around each one of these 3 contours. And as I mentioned before, there's nothing special about 3. We could have had 10, or n, but it's just a matter of how complicated a figure you want to have to make the point. So I just decided on 3. So we'll show what the integrals look like on the next slide. You might want to do a screen map of this figure just so you have it in hand when you're viewing the next slide. I was only able to fit so much on the slide, so I did the figure first, and then I'll show you the integrals on the next slide. So let's write down in terms of integrals what I said on the previous slide in terms of just figures. The first thing we had done, recall, was we took gamma and we broke it into gamma sub 1 and gamma sub 2. So our integral over gamma sub 1 of f of z is equal to the integral over gamma sub 1 plus the integral over gamma sub 2. And then for gamma sub 1, we use the deformation invariance theorem to find a alternate contour, which we called omega, and that was consisting of several subcontours, smooth curves. Then we did the same thing for gamma sub 2. We wrote that in terms of phi, and that was consisting of several smaller curves. And the reason we did that is because we got a lot of cancellation between these two alternate contours, and we were just left with having to take the contour about 3 circles about each one around each of these 3 singularities. So let's continue on the next slide. So writing things out, I pretty much said this on the previous slide. We replaced gamma with gamma sub 1 and gamma sub 2. And in turn, we replaced gamma sub 1 with omega and gamma sub 2 with phi. And then we noted that there was a lot of cancellation between the contours and the subcontours within omega and phi because they were going in opposite directions. And we were just left with these 3 circles to take the integral about. Yeah, and as I mentioned several times, there's nothing special about 3. We could have had n singularities, and then this would just be the sum over n terms. So we can play the same game with n singularities. We get this type of final result, and that's I just wrote this in terms of a summation formula. So this is the general formula where you have singularity Z1, Z2, Z sub n. They're all within our contour of interest gamma. And we go about finding alternate contours that comprise gamma, and then we get cancellation, and the problem reduces to taking the contour integral about a series of circles. And this is known as Cauchy's residue theorem. Now we'll go a little bit further in this theorem because we can actually describe how to find this integral, and we'll do that in the following slides. So we've reduced our problem to solving a series of integrals, each one about a singularity of the given function, and each contour is a circle. The solution is going to depend on the type of singularity, whether it's removable, a pole, or an essential singularity, and we'll cover those cases in a minute. What I wanted to mention here is that by the Theorem 140, which concerns the Laurent series, our function f of z is analytic in a punctured disk about z sub 0. So we have this Laurent expansion from where the indices go from minus infinity to plus infinity. Z sub 0 is one of our singularities, and then this is our punctured disk. And just one caution here is that we want to make the radii for each one of the singularities such that the punctured disk doesn't intersect any of the other punctured disks. But that's always possible because we only have a finite number of singularities. So we can always make this radius small enough so that the various punctured disks around each singularity don't intersect each other. And then once we have this, we can plug f of z into our integral for one of the contours about a circle. So we put this in here, and then we can bring the summation outside of the integral as well as the constant c sub n, and we're left with this problem to solve, which let me continue on the next slide. So bringing over the final equation we had from the previous slide, we have one integral of this form represented as a series for each of the singularities of our function within the contour of interest. And from example 2 in lesson 15, you may remember that we solved this contour integral about a circle, z minus z sub 0 to the nth power. And we had two cases. When n does not equal minus 1, the integral is 0. And when n equals minus 1, the integral is equal to 2 pi I. So we have something now to plug into our formula here, because this integral, we know the answer to it, and it's going to be 0 for almost all of the c sub n except for when n equals minus 1. So when n equals minus 1, you're going to get c sub minus 1 times 2 pi, the value of the integral, and that's going to equal our function here. And this c sub minus 1 is what's known as the residue of f at z sub 0. And we represent it with this notation, residue f at z sub 0. So that's what we need to find. If we can figure out what these residues are, then we can evaluate the contour integral about the circle for each given singularity, and then when we add them all together, we get the value of the overall contour integral that we had several slides back. And we'll do some examples to make this a little more concrete. So let's look at the case where we have an isolated removable singularity. In that case, all the coefficients of negative powers of z minus z sub 0 in the Laurent series are 0. So the residue of f at point z sub 0 would equal 0 when we have an isolated removable singularity. And for example, if f of z equals sine z over z, we saw that that was a removable singularity at z equals 0. And that tells us that the residue of sine z over z equals at 0 equals 0. And in turn, the integral of over the contour circle about z sub 0 equals 0 of sine z over z equals 2 pi I c minus subscript minus 1, and that is what we define to be the residue, and so that equals 0. So that was the easy case. When we have an isolated removable singularity, we always get the residue being 0. Next, we consider the case of a simple pole where we have, by definition, a Laurent series of this form here, where you just have a c sub minus 1 not equal to 0, and then all the other coefficients with larger negative indices are 0. We multiply both sides of this equation by z minus z sub 0. We get this. Then we take the limit as z approaches z sub 0 on both sides. And on the right, we see that all of these terms go to 0. And so we're just left with the c sub minus 1, which is the residue. And so we can compute the residue of a simple pole just by taking the limit as z approaches z sub 0 of z minus the singularity times the function. Okay, let's look at an example. Let's take the function f of z equals sine z divided by z minus 1 times z plus 2. So there we have two poles, one at z equals 1 and one at z equals minus 2. That follows from part 2 of Theorem 146. That was from the previous lesson, where we had equivalent conditions for identifying poles. Then we just use our result from the previous slide to find the residue of f at 1. We multiply by z minus 1 times f of z. We take the limit. So we have the limit as z approaches 1 of sine z over z plus 2, and that gives us sine 1 over 3. Then we do it the same thing for the singularity or the pole at minus 2. Take this limit as z approaches minus 2 of z plus 2 times f of z, which equals the limit as z approaches minus 2 of sine z over z minus 1, which equals minus sine of minus 2 over 3. So if we wanted to take the contour integral around this function, where the contour included our two poles, then the solution would just be the sum of these two multiplied by 2 pi I. And that comes from our Cauchy's integral theorem that we stated a few slides back. We have a second example of a simple pole here. We have f of z equals p of z over q of z, where q of z has a root of a simple root at z sub 0, which means that there's a simple pole for f of z. We also assume p of z sub 0 doesn't equal 0. Then we can write q of z in this form by factoring out the z minus z sub 0, and where h of z does not equal 0 at z sub 0. Then we can rewrite f of z like this. We just plugged in q of z in this form and then flipped the h of z to the top. So f of z has a simple pole at z sub 0. And then we can apply our formula for simple poles, which we derived earlier in this presentation. So we just take the limit as z approaches z sub 0 of z minus z sub 0 times f of z. And we can rewrite it like this. We just took the z minus z sub 0 and put it in the denominator, and then we subtracted 0, right? Q of z sub 0 is 0 because we assumed it was a root of q of z. So we have this, but then this is a definition of the derivative of q at z sub 0. And then we plug in z sub 0 into p of z, and we get this formula here. So we have a general formula of anything that is of this form that has the conditions we mentioned here. And we can use that in the next slide in a more specific example of a function that's taking this form. So keep this final result in mind as we go to the next slide. So let's make use of the result from the previous slide. We have the function here f of z equals tangent z, and that equals sine z over cosine z by definition. And we know the cosine z has zeros at pi over 2 plus or minus n pi, where n is an integer. And so these are essentially poles of order 1. And we also know that sine z does not equal 0 at these points. So we meet the condition of the formula we derived from the previous slide. And we can make use of that formula to derive the residue. So we take the derivative of cosine z, that's equal to minus sine z, and the residue of the tangent of z at all these different poles, simple poles, is a matter of taking the of evaluating the sine at the pole, and then evaluating the derivative of cosine z, which we know is sine z at that same point, and the sine of pi over 2 plus or minus n pi is 1, and then we have minus that on the bottom, so we just get minus 1. So for poles of order m greater than 1, we have the following theorem. If f has a pole of order m greater than 1 at z sub 0, then the residue of f at z sub 0 equals the limit as z approaches z sub 0 of 1 over m minus 1 factorial times the n minus 1 derivative of z minus z sub 0 to the m power times f of z. And we can prove that. First, we note that by the definition of a pole of order m, the Laurent series has this form here. It has m terms with negative coefficients, and then the rest of the terms with negative coefficients are 0. We multiply both sides of this by z minus z sub 0 to the m power, and we get this expression. And we need to continue on the next slide. So continuing from the previous slide, just rewriting our expression that we had previously. We take the derivative m minus 1 times on the left, we get this expression on the right, c minus m. Of course, the derivative is 0, and we take it even just once, but we take m minus 1 derivatives here. All these terms up to here go to 0, and then this term here is m minus 1 factorial times c sub minus 1. And then all the remaining terms after that have a z minus z sub 0 term in it. And you can see what we're going to do, taking the limit on both sides. We get the limit here of this expression. And then on the right, all of the terms except for the first one go to 0. And then we get our formula for the residue. I mean, we can divide by the m minus 1 factorial divided onto the left, and then we get our expression stated in the theorem. So let's do an example. We have this function f of z equals e to the z over z to the fourth times z minus I squared. So we have a pole of order 4 at 0 and a pole of order 2 at I. Use our theorem from the previous slide to find the residue at 0. It's 1 over 3 factorial, the third derivative of z to the fourth times f of z. So it's the third derivative of e to the z over z minus I squared. We get this long expression here, but there's a lot of cancellation. When we put in 0, we get this is 0, this is 0, that's 0, that's a 0. So you get e to the 0, which is 1 times minus 18 minus 17i. It's divided by minus I to the fifth, which is minus I, and then I multiply top and bottom by minus I to get this final expression. Then we do the other residue at I. We take the derivative of z minus I squared times f of z. You get e to the z over z to the fourth. You take the derivative of that and plug in I. And I did some simplifications, and you get e to the I times 1 plus 4i. And just as a hint, you can do some of these derivatives via symbolic computation programs like Wolfram Alpha. There's a few other ones that'll do that, and so that'll help move things along. The main idea is to get the result here, and these derivatives can get quite tedious and error prone. Okay, we have an exercise for the listener. Take the function f of z equals sine z over z cubed times z minus 1 squared, and find the residue at z equals 0 and z equals 1. And if you want to check your answer, I just put the solutions here. So let's do one final example, and that's of finding the residue of an essential singularity. The way we do that is we find the Laurent series, and then the coefficient c sub minus 1 is actually the residue. So let's see what that looks like for an example. We have f of z equals z cubed times e to the 1 over z squared. So first we put in 1 over z squared into the Taylor series for e to the z, and we get this expression. Then we multiply by z cubed, and we get this, and so let me just circle this here. So this is our coefficient c sub minus 1, and so this is the residue, and we've solved the problem here. So the residue is just the 1 over the 2 factorial, which is 1/2. Okay, so that's the end of this lesson, and hopefully you gained some knowledge here in terms of residues, but also in putting together a lot of the concepts like series and integrals and derivatives, so forth, that we went over in earlier lessons.